lab report that was done by a student. So you do have to go kind of through the whole thing. I mean, you don't have to read through the whole thing, but you have to just scroll through it to get to the conclusion. And then right at the bottom, here we go, is a sample conclusion. So this is a really well done conclusion. It's part of a lab that we did not do, but another class did. And I think it does a really good job of like integrating what they saw with what they're inferring. The conclusion really is all about making inferences based on your data and what you did in relation to the goal of the lab. So the first paragraph says, in the first part of this lab, a piece of zinc was placed in a beaker of water and was trapped under an inverted test tube filled with water. There were no changes observed. As 2 drops of phenolphthalein were added into the beaker, again, no changes were observed. As a result, we can infer that zinc does not react with water. So although the procedure and observations are discussed, it's in relation to the inference of, as a result, we can infer that zinc doesn't react with water. So there's this inference here, and it's backed up by this information. So basically, a lot of people just really summarized in the conclusion, like summarized what happened in the lab, and then didn't really write much about any inferences or anything that actually would be an interpretation of that data. So it is okay to summarize what you did and talk about what you did, procedure and observations, but just make sure that you're making some kind of inference based on that. Does that make sense? Okay, and this one, honestly, like, it's really nice. It's brief and it summarizes the lab well. I think if you just read the conclusion of this lab, you'll get the idea of what the people did and what the goal of the lab was, and that's kind of the goal of a conclusion. So if you have a look through this one, I think that would be a good idea, and then just kind of look at what your lab is compared to this. And there is also that lab how to write a conclusion thing on the Google Classroom. So that is that. Okay, cool. Yeah, and try to have that done by tonight, please. Tomorrow at the latest. So 7.2, stoichiometry calculations. So now we're looking at mass, moles, volume, and molecules. All the fun stuff. So in stoichiometry calculations, this is where we're actually going to figure out how much of a chemical, so we'll just call chemical 1. The notes are just up here, or somebody at your table might have grabbed them for you. How much of chemical 1 there is in a reaction based on the amount of another chemical, which we'll call chemical 2, involved. And we need to know the mole-to-mole ratio. Of these 2 chemicals. So that is the key step to all of the calculations that we do in stoichiometry. Mole-to-mole ratios, very, very, very important. It is the bridge between the 2 chemicals. So this diagram just kind of shows the connections that we can make with stoichiometry calculations. So I could say, if you have got 10 grams of zinc, how many moles of hydrochloric acid would you need to react with that? Or I could say, in order to make 1 liter of soap solution, how many molecules of olive oil would I need? So you can start moving between molecules, volume, mass of 2 chemicals, and using this bridge based on the ratio. So this diagram, I'd recommend putting that on any like information sheets or anything that you're going to use moving forward. Does this diagram make sense to you guys? So it's just like a reactant to product thing, or this can even be on one side of the arrow. We'll reference this as we go through some of these examples. Okay, so question number 1. How many moles of sodium metal would be needed to react with chlorine gas to make 737 grams of sodium chloride? So again, the first thing we need to do is what we've been doing for the whole last unit, pull out the equation for this and balance it. This is what type of reaction? Sodium metal and chlorine gas to make sodium chloride. Yep, awesome. So that's a synthesis reaction. Okay, so we're going to go sodium plus chlorine, diatomic, sodium chloride. Oh, we do have the states. And then if we balance this, got 2 and 2. Okay, so step 1, balance it out. Then we're going to convert the grams of sodium chloride. I'll zoom in on this a little bit. Or actually, I'm going to just write down like what we want and what we need here. So we know that we want to make 737 grams of sodium chloride. And what we're asked for is how many moles of sodium metal. So I really like to write out the equation and then write out your knowns and your unknowns just right underneath it there. I find that that's a really useful way to do it, really good way to organize. Okay, so ultimately what we always need is the mole ratio and the number of moles. So we've got a ratio. We know it's a 1-to-1 ratio, 2 sodium chlorides for every 2 sodiums. And we know how many grams of sodium chlorides there are, but we do not know how many moles there are. So the first step is to convert our 737 grams of sodium chloride to moles of sodium chloride. And if we just take a quick peek at this chart, if molecule 1 is sodium chloride, we've got a mass. We're going to go to moles. We're going to use our bridge, which is our ratio, and we'll get moles of our sodium. So once we've got our moles of sodium chloride, we will know our moles of sodium using the mole bridge. Molar mass of sodium chloride is 58.5 grams per mole. And then for the rest of the calculation, so if I know I have 737 grams, or I want that, of sodium chloride, then I'm going to multiply that by my ratio, grams per mole. So 58.5 grams per mole of sodium chloride. That's canceling out my grams and just leaving me with moles. And then I've got a 1-to-1 ratio. So for every 1 mole of sodium, there's 1 mole of sodium chloride. That gets rid of my moles of sodium chloride and turns this into moles of sodium. You could also write 2 to 2 here. Either way is going to work just fine. And what you're going to end up with here is 12.6 moles of sodium. So that's how many moles of sodium you need if you're going to react these two things and make sodium chloride. Fun. Can I flip this over? I'll give you guys a second. Okay. Alrighty. Step one of our next one. It's going to be the same as this one. So this one's asking us how many grams of potassium chloride are produced by the decomposition of 118 grams of potassium chlorate. So we know that this is a decomposition reaction of KClO3, and that is going to go to KCl and O2. So this is decomposition. Okay, and when we balance that, we should get 2, 2, 3. Okay, so what do we have? Yep, mass. So we've got 118 grams, awesome, of kale potassium chlorate. So we have 118 grams of that, and we want to know how many grams of potassium chloride will be produced. So if I reference this chart on the first page that we looked at, chemical 1 here is the potassium chlorate, and we've got mass. So we're going to need to go to moles of potassium chlorate, use our mole ratio to get into potassium chloride, and then go to mass of potassium chloride. All right, so we're converting into moles. And then to moles of KCl using the mole bridge. Mole bridge coefficients. And then we're going to go from the moles of KCl to grams of KCl. Okay. First thing, I need the molar mass of potassium chlorate, and I need the molar mass of potassium chloride. I am going to give you those. No, do you guys know, does anybody know why you wouldn't just be able to keep it in grams? Well, here, I'll actually show you. I will explain it as soon as I've written this out. Okay, so for every 1 mole of potassium chloride, it's 74.6 grams. For every 1 mole of potassium chlorate, it's 122.6 grams. So if I were just to go, like, there's 2 grams of potassium chlorate for every 2 grams, or sorry, if I were to do like a 1-to-1 ratio with grams, I would be saying that this means there's 118 grams of this, right? But because this molecule is so much heavier than this one, you can't just convert it with grams. We need to know like how many of them there are, because essentially what we're seeing is like they're reacting at a 1-to-1 ratio. So 1 molecule for every 1 molecule. And 1 molecule of each doesn't weigh the same amount. Does that make sense as an answer to that? Yeah, so we always have to go to moles. Really important. Okay, so those are our 2 molar masses. So we're going to make a whole long string of fractions now and use our unit conversions. So we're looking for the grams of KCl. We don't know what that is. So what we're going to start with is our known, which is 118 grams of potassium chlorate. I'm going to multiply that by my molar mass of potassium chlorate, which is 122.6 grams per mole. That cancels out my grams. Then I'm multiplying that by, it's a 1-to-1 ratio for moles. I'm just writing the 2's. Okay, so you can write 2 to 2. You could also write either of those. Both of those things are fine. Both of those are okay. In the math, when you do the math, they're going to come out the same way. I just find writing the ones a little bit easier. Technically, there's 2 for every 2, so this one's more technically correct, but this one just makes doing the math a little bit easier. Okay, and then last thing I'm going to do, so I've gotten rid of KClO3 now, and I'm into moles of KCl. So now I've got to go last step into grams of KCl by using the molar mass. So 122.6 grams, whoops, wrong one, 74.6 grams for every 1 mole of KCl. And what that will give me is 71.8 grams of potassium chloride. So produced by this reaction is 71.8 grams of potassium chloride. Yeah. Any questions about how I got from this to this? Okay, and if you're somebody who does not like setting up these fractions and you have a different way that you go through this, that's totally okay. It's up to you as long as you're getting the right answers. Or if you have a different way, all is good. Okay, next one is a combustion. So this is a hydrocarbon combustion of propane gas. So anytime you are barbecuing or using propane for anything, this is what is happening. For every 1 molecule of propane, you have 5 molecules of oxygen from the air coming in, and you produce 3 molecules of carbon dioxide and 4 molecules of water. Just from knowing that reaction in real life, do you guys think this is an endo or exothermic reaction? Yeah, it's exothermic. It's a combustion reaction and it produces heat. Yeah. Okay. If a sample of propane is burned, what mass of water is produced if the reaction is producing 50 liters of carbon dioxide? So somebody's taken this reaction and they have captured the carbon dioxide gas that was produced and measured it to be 50 liters at standard temperature and pressure. And they want to know how much water did that produce in grams. So I'm going to start off by just writing out this reaction. And what I know and what I don't know. Okay, so I know that there are 50 liters of CO2 produced, and I want to know how many grams of water are produced. I do not need to know anything about how much of these two there are because it's telling me 50 liters of this is produced. And I've got a ratio for products. So we're just looking at these two. We don't need to know anything about these other two. Okay, so what are we going to do here? If we want to know grams of H2O, we're going to start with our known, which is 50.0 liters of CO2 at STP. Okay, now we're going to have to take our brains and turn them back like 2 units. And remember how many moles there are in every liter of gas at STP. Do you guys remember that? Nice. 22.4 moles of CO2 for every 1 liter. All right, and that's going to give us how many moles of carbon dioxide we have. Didn't even need to use the molar mass. How cool is that? Pretty cool. Okay, and then we're going to go, what's our ratio? We've got 3 carbon dioxides for every 4 waters. So now we're going from carbon dioxide moles into moles of water. So I'm going to go, what's that? Oh my gosh, thank you. Wait, 22.4 moles per liter. No. Yeah, no, you're right. Sorry. 22. 1 mole is 22.4 liters. Oh my gosh. Yeah, there we go. Thank you. Upside down numbers. Okay, so we're multiplying that. And then we will have canceled out liters of carbon dioxide. Next up is going to be our ratio here. So going into water. So we're going to do 4 moles of water for every 3 moles of CO2. And that's going to leave us with moles of water rather than CO2. And then we need to use our molar mass of water finally to get to grams. And there are 18 grams of water for every 1 mole of water. And that is finally canceling out moles and giving us grams. So at the end there, we are going to be left with 53.6 grams of water. So that is how many grams of water are produced if you take the time to measure out 50 liters of carbon dioxide gas produced. Whew, that's a lot. Okay. Any questions about this process? Well, okay, I'll give you a second and then I'll go to the next question. Okay, so there's going to be a part B to this, which is how many molecules of CO2 are produced if a sample of 1.35 times 10 to the negative 6 grams of propane is burned. I'm just going to rewrite the equation above this so we can reference it. It is C3H8 plus 5O2 CO2 plus 4H2O. Okay. So how many molecules of carbon dioxide are produced if this many grams of propane is burned in the presence of excess O2? So that means that we've got more oxygen than we need. So there's tons of oxygen. What that is telling us is we know that some O2 is going to be included in the reaction. And C3H8 does not burn without oxygen. So basically, it's telling us that we don't need to worry about the amount of oxygen being used. So we can simply assume that there's enough to make all of that propane that is present react. So sometimes you'll be given the number of moles of this and the number of moles of this, and one of them is going to be limiting the other one, and you're going to have to figure out which one is which. This is just telling us there is so much oxygen, we do not need to worry about it. Okay, so we have got 1.35 times 10 to the negative 6 grams of propane. We've got enough enough oxygen to deal with that. And we want to know how many molecules of CO2 are needed. All right. So if we look at our chart back here, what we're doing is going from mass of propane, and we're going to need to go to moles of propane. We're going to need to use our ratio and get over to moles of, are we looking for water? Carbon dioxide. We're looking for carbon dioxide. Yep. Moles of carbon dioxide and then molecules of carbon dioxide. So we're going like that. Okay. So in order to find that, if you want to abbreviate molecules, you can go MOLEC. Just don't confuse that with moles. Throw a C on the end. So molecules of CO2, 1.35 times 10 to the negative 6 grams of propane. And then first step, again, is we have to get that into our number of moles of propane we have. So our molar mass, you guys could calculate this if you wanted, but we've got 1 mole of propane weighs 44 grams. And then we have a 3-to-1 ratio, so 3 CO2s for every 1 C3H8. So far we've canceled out grams of propane, and now we've canceled out it being propane. So we're into just CO2 now, and we're going to molecules. So if we know how many moles, I should have written moles there. Okay, if we know how many moles of CO2 we have, what's that number that we use to get to molecules from moles? Awesome. So in every 1 mole, there are 6.022 times 10 to the 23 molecules in 1 mole. So that's going to be our last thing that we need to cancel out. And if we do all of this correctly, what we should end up with here is 5.54 times 10 to the 16 molecules of CO2. And then, yeah, just a note, oxygen is not in that calculation. It does not need to be there because we just have so much of it that it completely reacts. Hey. Any questions about that before we get into doing some practice questions? This book here? 1 second. Okay, are we all comfortable with that? I have got some student textbooks around the room.
No, I'm looking for the teacher version of that.
Oh, yeah, that one is